In 1986, one of the most consequential physics demonstrations of the century required no laboratory. It took a small clamp, a piece of rubber, and a glass of ice water. With those three objects, Richard Feynman showed a presidential commission why the Space Shuttle Challenger was destroyed, and exposed a deeper failure hidden inside a mathematical model. Chapter 12 of Classical Mechanics studies momentum and the flow of mass, the physics of rockets. The chapter opens with Robert Goddard describing the first liquid propellant rocket flight. On the 17th of March, 1926, the rocket rose slowly, then moved at express train speed, and to Goddard it looked, in his words, almost magical as it rose, without any appreciably greater noise or flame, as if it said, "I've been here long enough. I think I'll be going somewhere else, if you don't mind." 60 years separate that first flight from the disaster this preface examines. That disaster came in 1986, when the Space Shuttle Challenger was destroyed. The Rogers Commission was convened to investigate. One of its members was the physicist Richard Feynman, and during the public hearings he made an extraordinary demonstration. Feynman believed he had found the cause, and it centered on one small component, the rubber seals, called O-rings, in the joints of the solid rocket boosters. The role of the O-rings is to seal the joints of the solid rocket booster. When the fuel inside the booster starts to heat up, it expands and pushes against the sides of the booster. The walls strain, and if a joint has an opening, the hot gas inside tries to escape through it. The rubber seal's job is to expand and close that opening as it forms. The seal works only if the rubber stays springy, able to swell into a gap the moment the gap appears. Feynman had learned a critical fact about that rubber. It failed to expand when the temperature dropped to or below 32 degrees Fahrenheit, which is 0 degrees Celsius, the freezing point of water. Challenger flew on the coldest morning in shuttle history, the air barely above freezing, the joint colder still. The seal that had to stay springy was sitting at a temperature where it had lost its spring. Feynman believed he had found the cause. What he needed was a way to test it. His test was simple and public. During the hearings, Feynman took a piece of O-ring material and squeezed it with a C-clamp, simulating the compression the seal experiences inside the shuttle joint. Then he dropped the clamped rubber into a glass of ice water. Ice water sits at 32 degrees Fahrenheit, near the launch day temperature, for as long as ice and the liquid coexist. When the clamp came off, the chilled rubber failed to spring back. At the temperature of that morning, the material meant to chase a moving gap could not recover its shape at all. With the seal unable to respond, the physics of the failure is familiar. Hot gas under pressure behaves like steam in a tea kettle. Give it an opening and it streams out through that opening, the spout. In the booster, the cold O-rings could not expand to fill the gaps in the joints, so a joint became the spout. Hot gas began escaping through the side of the booster. On Challenger, that leak was not hypothetical. It was visible, a small flicker caught in a photograph of the launch. From that flicker, the chain of failure runs straight through to the loss of the vehicle. The flicker grew into a flame. The flame heated the external fuel tank until the tank ruptured. The rupture released liquid hydrogen into the atmosphere, where it exploded. The fireball engulfed the stack, and moments later, Challenger broke apart. As Feynman explained, because the O-rings could not expand in that near-freezing weather, the gas found gaps in the joints, and that led to the explosion. Every link in this chain is ordinary, traceable physics. A cold seal, an escaping gas, a flame, a rupture, an explosion. The glass of ice water explained the accident. The deeper lesson came in an appendix Feynman wrote for the Commission's report, titled Personal Observations on the Reliability of the Shuttle. Before the disaster, the booster O-rings had been observed eroding, hot gas eating into rubber that was, in Feynman's words, not designed to erode. He was blunt about what that meant. Erosion was a clue that something was wrong. Erosion was not something from which safety can be inferred. Feynman went further. There was no way without full understanding that one could have confidence that conditions the next time might not produce erosion 3 times more severe than the time before. The erosion varied peculiarly from case to case, and nobody understood why. Nevertheless, he wrote, officials fooled themselves into thinking they had such understanding and confidence, in spite of the peculiar variations from case to case. The claimed confidence rested on something specific, a mathematical model, and that model is where this story becomes a lesson in method. The model worked like this. Suppose a stream of hot gas impinges on the O-ring material. The heat delivered to the rubber is determined at the stagnation point, the spot where the stream comes to rest against the surface. Up to there, Feynman noted, the model rests on reasonable physical thermodynamic laws. Then comes the leap. To determine how much rubber eroded, it was assumed that erosion depended only on this heat, through a formula suggested by data on a similar material, not the O-ring rubber itself and not any physical theory of how rubber erodes. Here is where the exponent came from. Plot the data on logarithmic axis, the logarithm of erosion against the logarithm of heat. On such a plot, a power law becomes a straight line, and the slope of the line is the exponent. The logarithmic plot of the erosion data suggested a straight line, so it was supposed that the erosion varied as the 0.58 power of the heat, the 0.58 being determined by nothing deeper than a nearest fit to the scattered point. Then, adjusting some other numbers in the formula, the model was made to agree with the observed erosion. Erosion reaching depths of up to 1/3 the radius of the ring. Feynman's verdict on this procedure is the heart of the appendix. There is nothing much so wrong with this as believing the answer. Uncertainties appear everywhere. Look at the fitted data honestly and the problem is plain. The points form a cloud around the line, some lying twice above the fitted curve, some twice below it. That scatter is information. It says that an erosion twice as large as the model predicted was entirely reasonable, not an outlier, just the ordinary spread of the data. And similar uncertainties surrounded the other constants in the formula. The model had a precise exponent and an imprecise grip on reality. Separate the two things the model contained. The physics, hot gas, stagnation heating, was sound as far as it went. The fit, the 0.58 power law, was a summary of scattered data, and nothing more. An empirical curve fit is not physical understanding. It interpolates the cases it has seen. It carries no authority about the next case, and its scatter is a measurement of its own unreliability. When we use a mathematical model, we must give careful attention to the uncertainties in that model and report the prediction together with its spread. The lesson survived the investigation in one sentence of Feynman's. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. Feynman's glass of ice water and the appendix's cloud of scattered points make the same argument at two scales. The rubber did not care what the model asserted, and the erosion did not stay on the fitted line. This preface opens a chapter on momentum and the flow of mass, the physics of rockets. The equations ahead are powerful. Challenger is the standing reminder to carry their uncertainties with them. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.